Good afternoon, everyone, and thanks, Ivan, for giving me this opportunity sharing my work with you. And today, I'm going to talk about my work, which is collaborated with Professor Huang when I was in medicine. And the topic is about network layer support for Gigabit TCP flows in wireless mesh network. So in today's talk, first I will introduce the motivation and challenges in supporting the TCP flows in the wireless mesh network, and then I will describe our proposed spare bandwidth rate adaptive network coding scheme, which I will just call it as SRNC in the rest of today's talk. And eventually, based on the evaluation result, we can discuss about how the SRNC works and what could be applied by using SRNC or what will happen in the future. I believe everyone knows today people ask for higher and higher data rate for different purpose. For example, some people may want to download videos or watch movies, even though when they are on the move. These kind of applications actually have two characteristics. One characteristic is they are long-lived. For example, if you are watching a movie on your device, it may take more than 1 hour. And the other characteristic is it requires high bandwidth, especially based on the development of the technology. In the future, we would assume maybe it will require more than 1 gigabit bandwidth. So, to support this kind of applications, we may require high physical layer data rate, which can provide more than 1 gigabit bandwidth, and also require some other technologies and higher layer support, because everyone must know that in the network protocol there will be more than one physical layers which support the whole packet delivery. So that's why these two ideas will be considered together in order to support the TCP flows in the gigabit level. So first, you may think then why mesh network? It is because mesh network is kind of a promising approach to provide high physical layer data rate. But providing high, more than 1 gigabit bandwidth is not enough, because in the whole wireless situation, the channel condition changes dynamically. When the network condition changes, the traffic flow may have traffic congestion or wireless loss, which will result in the throughput or the performance degradation. Especially when the link rate, the data rate is more than 1 gigabit per second, the degradation will even worse, even severe. Let's see a simple example by this topology. We consider if there will be just 10 TCP flows sent from the node G through the small network to the node A, and in the network at the same time there will be cross traffic share the link bandwidth between the node H and I. You may know that when there will be a lot of traffic in the network, the performance must go down. And based on this figure, we can find that even though the network, there are 3 bars in this figure, and the red bar is used the traditional new TCP protocol, and the yellow bar is more supporting high bandwidth delay products. Is more most recent TCP protocol called compound TCP. And the green bar is the max flow rate in the network. And the x-axis is the link bandwidth in the network. And the y-axis is the achieved TCP throughput. You can find in this figure that although the max flow rate stays the same, the TCP throughput drops significantly especially when the link data rate is more than 1 gigabit per second. Then
this is with constant loss rate, or
this will no, here it's just pure congestion loss. Yeah. So like when the cross traffic share the link bandwidth, then traffic congestion may occur when the link bandwidth goes down, and then TCP may need to react for the sending rates. Under this condition, the total average throughput decreases. So that's how this simple example obtains. So then how could we enhance the TCP performance? So in this work, we proposed the SRNC scheme, which contains 4 ideas. The first one is digraph diversity, which is related to multipath routing, and then interflow network coding, spare bandwidth exploitation, and then buffer management. Before I start describe these 4 ideas, let's see some related work that has done in the literature. So in reality, packets are forwarded in single path routing. For example, if the 2 packets want to forward it from node A to node H, normally there will be just pick one specific route and then forward it. And many research have shown that multipath routing can increase the performance, especially when the link bandwidth is congested or something. So instead of using single path routing, when the packets in node A, it can choose more than one routing path to forward the packets. Under this condition, if link congestion occurs in any specific link, the performance still can be enhanced. However, it has been known that to find the routing path for in a routing topology, the cost will be very expensive. And if link congestion occurs, rerouting needs to explore the whole network topology again, which would take time, and this may limit the performance enhancement. On the other hand, you may know that FEC has been used to enhance the transmission reliability by sending more packets in the network if there is spare bandwidth. For example, for the yellow packets in this network topology, instead of sending one yellow packet, the node A can generate more, like 2 yellow packets and then forward it to the destination H. Because of these extra yellow packets, even though the packet loss occurred in the link BF, the node H still can receive the yellow packet successfully. However, we may know that to find how many redundant packets to send in the network will require the feedback information, which takes delay time or some other computational complexity. And also, if we just do some simple algorithms or mechanisms to generate the redundant packets, if too many redundant packets sent into the network, it will cause the traffic congestion in the network, which will decrease the performance. On the other hand, if few extra packets sent into the network, the performance enhancement is limited. So, under this situation, we would we want to adapt the network coding with the previous 2 schemes. Network coding has been known to increase data rate for multicast transmission. You may read like tons of paper for that, like since 2000 or 2010. But here, we adapt the network coding with the previous two ideas for multiple TCP flows in a routing diagram instead of doing multicasting. By borrowing this network coding idea, the SRNC can adaptively to control the packet transmission into the network based on the change of the network situation without any feedback information. So now let's talk about the four ideas of the proposed SRNC individually. The first idea is the digraph routing. The idea of digraph routing is when the gateway node receives multiple TCP packets from the internet, it will base on the destination to find the routing digraph and then forward it. For example, if the node A received packets from S1 and S2, it will find a routing digraph. For example, this will be the routing graph found by the gateway node A because D1 and D2 connected to the mesh node. We can say this access node G. And specifically, the number indicates the bandwidth as a simple example to indicate the bandwidth for each link. So when A, based on D1 and D2 find this routing digraph, it will just forward it. That will be the first idea of digraph diversity. And then we combine it with interflow network coding. The interflow network coding means packets are network linear combined together across multiple TCP flows. And each node will do network coding before forward the packets to its outgoing links. Let's continue the example shown previously. So when A received the 4 packets from S1 and S2, it will linear combine it and generate like it received 4 network coding, 4 packets from the internet, and then it generated 4 linear combined network encoded packets, and then forward it to its next hop. And then when the access node G received the network encoded packets, it tried to decode it. If it's decoded successfully, it will forward it to the destinations. However, because of this linear combination, or you can say it's network encoding scheme, during the transmission, if any packet lost, it may result in the packets are undecodable. And for this case, the 4 packets may be just totally discarded, which means instead of losing 1 packet, you lose like 4 packets in this case. Then, how could we do if, since the network still have available bandwidth? You must know the answer. Then why can't we just send the redundant packets? So then it comes the third ideas of exploiting the available bandwidth. So when A receives these 4, when A generate the 4 network encoded packets, it forward the packets not only depends on how many packets it's received, but also depends on the outgoing link it has. As a result, when the packet is forwarded through the whole network, the G will receive, because of the spare bandwidth in this network, G will receive more than 4 packets. And then definitely it can decode it and then forward it to the destinations. Then you may ask, what will happen if there is a cross traffic? Or it's like kill other traffics in order just to sustain the TCP flows? Yes, we don't want this kind of ideas to happen. So how could we control the number of redundant packets in the network? Then we need buffer management to properly fair share the available bandwidth with the cross traffic. Then how the buffer management is executed. So when the gateway node generates the network encoded packets, it will mark several high priority packets. And those high priority packets won't be more than this number of high priority packets afterwards. And then at each step, when the packets forward the packets to its outgoing link, it will forward high priority packet first. If there is a spare bandwidth, it will generate a duplicate packet by the linear combination of its received packets. Since it's extra, which means even though it is dropped, it won't hurt the whole transmission or the decoding. Under this condition, we mark it as low priority packets. That's how the packets are prioritized and forward on each mesh node, or you can say the transmission node. So, like in the presence of the cross traffic congestion or buffer overflow may occur. When it occurs, we need to drop some packets, and then the low priority packets will be dropped first instead of just drop the incoming high priority packets or the incoming packets from the cross traffic. Under this condition, the fair share for the bandwidth across different traffic flows can be sustained. To combine these four ideas, we can see that node A forward the packets, and even though there are some packet loss during the transmission, as long as the access node G can receive sufficient number of packets for decoding, it still can reconstruct the original packets and forward to the corresponding destinations. And this is how the SRNC works, incorporate with like different ideas. To sum up, for SRNC, the packets are routed first is routed in a digraph, or you can say it is multipath routing. And then packets are network encoded across different traffic flows instead of like from the same traffic flows. The ideas for network encoding across different traffic flow is if, unfortunately, the packets are undecodable, per traffic flow, it will just reflect one packet loss instead of like more than one packet loss for one specific TCP flows. And you may know that for more than one like packet loss for TCP, it will like cut the transmission, the congestion window a lot. Then it will like decrease the throughput dramatically. That's why we use interflow network coding instead of intraflow network coding. And for each node in the network, it will network encode the received packets before forwarding to its outgoing link, and it will send as many as possible based on the spare bandwidth. And to proper manage the number of redundancy in the network, we have buffer management to conditionally discard some packets. Then A, the performance can be sustained properly for TCP flows. B, the cross traffic which does not apply SRNC can still get the performance which is the same as no network coding or no SRNC is applied for this whole network. So, anyone has questions before we see the evaluation part to see how the SRNC is performed? Okay.
What percentage of redundant packets do you expect?
Well, as I mentioned, it will depend on the spare bandwidth in the network. Yeah. And normally, for example, we won't generate the redundant packets more than 50, which means if I receive 3 packets, totally, at most, I will just send 6 packets to to my outgoing link. Yeah. Anyone else?
So does every router will do the recoding?
You mean encoding or decoding?
Encoding.
Yes, every node in the every step in the transmission, it will do the network encoding. But it won't. But network decoding only happens at the access node, which is the last step during transmission. I mean, the access point or mesh node connected to the destination.
Will this cause
Mhm.
unnecessary computational time?
Oh, well, because our encoding scheme will be just simply linear combination, and we don't do any sophisticated encoding scheme. And in the next few slides, there will be one slide which we do some hardware implementation to measure the throughput of the network coding, and we can discuss it later.
So, when the packets come in via G, G is network, G is encoding it, and so are C, H, F, or is it only G that is encoding it and A that is decoding it?
A is the one only do the decoding,
Yes.
and for the rest of packets, they are network. They need to perform network encoding.
All of it.
All of them.
Okay.
Yeah, but only G decides which packets need to combine together. Yeah. Anyone else? Okay, let's move forward. So this evaluation is done in NS2. I implement the SRNC in NS2 because at that time we don't have any access point who can support gigabit throughput. For per TCP flow, which needs 1 gigabit per second throughput, the access point need to support more than 1 gigabit data rate. So at that time, we don't have this kind of capability. I just do that in the NS2. And this is the simulation topology I used. So that will be similar to the simple example I showed previously. There are 10 TCP flows sent from the internet. And then at the gateway node G, it's combine multiple packets from different traffic flows and do the network coding. And then forward to the rest of mesh node in the network, in the topology. And the access node A when it receives a certain number of packets, or it will try to decode packets. If it is decodable, it will forward to the corresponding destination. If it's not, it will discard the undecoded packets. And the link bandwidth between each link, the average is X. It's because the link bandwidth sometimes, if the channel quality is good, it goes up. If the quality is bad, it goes down. So the average, we control it as X. And there is a link bandwidth between the access node and the destination is 1 megabit per second. And at the same time, there will be a cross traffic comes on and off from the shared link I and J. That will be the whole configuration for the simulation.
So, excuse me, in your model, how many MAC domains do you have? Is it using 802.11n or AC or something like that? What is the underlying?
Oh, here, we don't do specific. Initially we assume L2.11 AD, but at that time we don't.
So
there is no interference between the links on the mesh?
No, here we assume the interference is managed properly in the physical layer. So we only consider the transmission in the between the MAC layer and network layer domain to see how the functionality works.
So these are independent links?
Yeah, they are independent links. Yeah. Anything else? Okay, so first let's see that how SRNC performs under different link bandwidth. As the example shows at the beginning that the TCP throughput drops significantly when the link bandwidth increase. So here we do just scaling the link bandwidth and then to measure the performance for SRNC comparing to like three well-known schemes in the literature. The first one is multipath routing. It will be just simple like multipath routing. And the second one is do packet reordering. Because when we do multipath routing, TCP will also suffer for packet disorder at the receiver. So here we compare, since network coding is kind of hide this kind of packet disorder situation, so we compare the packet reordering as well. And the third one is proposed by Professor Madar from MIT. They have a network coding mixed TCP paper which do intra-flow network coding from the sender side and then also manage the redundant packets at the same time. And we also compare their works in our evaluation. And the x-axis is the link bandwidth in the mesh, and the y-axis is the achieved TCP throughput. And here we kind of simulate three different scenarios. It's like large spare bandwidth, moderate spare bandwidth, and tight spare bandwidth. We kind of control the different spare bandwidth based on the link bandwidth between the access node and the mobile host. We fix the link bandwidth, fixed X. We set it as 10 gigabit per second on average. And then we change Y to evaluate the performance, which means at the beginning when the link bandwidth, when Y is just about 500 or 600, the network will have like sufficient spare bandwidth because the bottleneck is on the last hop transmission. But when Y increase to 1.5 gig, it means the bottleneck becomes the network itself, because for 10 TCP traffic flow to share the link 10 gigabit per second of the link bandwidth, on average, theoretically, each traffic flow should just share around like 1 gigabit per second throughput or bandwidth. That's why we kind of simulate like three different scenarios for the available bandwidth. So it can be found that our proposed SRNC can obtain the highest TCP throughput. And also actually for SRNC, compared to the JK 2009, we don't need any feedback information to manage the number of redundancies sent into the network. And that makes SRNC even consolidated during the transmission when the network situation changes dynamically. And that's how the SRNC performs, or how SRNC can enhance the performance under different network situations.
Question on that.
Mm-hmm.
So the JK 2009 PRO and MR,
Mm-hmm.
did you implement them yourself or did you have implementations in an S2 from the authors?
For the MR, it is the default multipath routing in NS2 itself. And for PRO, I just do the packet reordering at the receiver side by myself. And for the JK 2009, I implement by myself from the sender side to do network coding. And then for this part, I'm kind of doing like ideal case that I know the network situation in advance to control the number of redundancies sent to the network. So it's kind of the best case JK 2009 can achieve in each case. Yeah.
So, question.
Mhm.
So, why is SRNC better than JK 2009?
A is because the number of redundancy is controlled by each node in the network itself, which can instantly react to the change of the link bandwidth, because JK 2009 is control the number of redundancy in the source part.
Link bandwidth is changing constantly.
No, it will change dynamically, but to know the network situation, you may need certain number, different link may not change at the same time, right? So when the sender into JK 2009, it knows the previous transmission, the network situation of the previous transmission. It's, for example, it thought maybe I could only generate 2 redundant packets. But when it's routed to like certain hub of the network, that link may have like quite low bandwidth. And then it will lose, it either create the congestion for transmission or it will just get dropped.
So what is the model for the changing the link rate?
Here I use a Pareto distribution to change the link bandwidth.
You mean you change the X?
Yeah, I changed the X, but to sustain the average X to 10 gigabit per second. So it will vary between 800 megabit per second to 1.2 gigabit per second. Yeah.
So you say the JK 2009 is doing the adaptive network encoding inside each flow, right?
Right, and at the sender side, and it won't do any extra encoding or generate any extra network coding packets during the transmission after the packet is sent out from the sender.
So the most biggest advantage from your scheme over their scheme is that for each after each link transmission, you do adaptive again, right?
Right.
Still inside each flow, right?
No, it's across different traffic flows. That would be another advantage we got, which is different from JK 2009, because if packets is undecodable, and since the packets are network encoded from different traffic flow, those dropped packets which are undecodable, for each flow it will just think I lost 1 packet. But for JK 2009, it will be considered like I lose more than 1 packet.
Because of the multiple.
Because they were encoded packet from the same flow. They encoded at the sender. So, for example, if on the sender I never encoded 5 packets, and at the receiver I decode it, and it's undecodable, I lose 5 packets. But in SRNC,
No, but I think the scheme is you send 5 packets, and the 5 packets is basically you have a congestion window size of 5, and then it will still report that I have received 4 encoded packets, so it will just it will just consider that there are 4 packets in flight and
Right.
send another one.
but because you keep continuously waiting for packets, right? Because it will just send extra packet out, and those 4 packets may get into another situation called timeout. Because for TCP itself, it will think I lose 1 packet, and I retransmit it. But actually, the rest of 4 are also not received, and each packet has a.
We'll send that 1 packet,
Mm-hmm.
and the next time the receiver receives that, they can see that with this 1 packet, I can decode along with the last 4 and receive.
No, but that is because the rest of 4 packets are received, right?
Yes.
Yeah, but if now the situation is I don't have enough linear combination, and those, at least I lose 1 or more than 1 packets.
Right. So that's why network coding is used. We don't have to know which packets are lost.
Right.
We just know that we
Right.
just need 1 more packet,
Yes.
and then the sender just regenerate a linear combination. And
Right.
when the receiver gets that,
Yes.
it knows, basically can try that to see if this packet is beneficial to the current session. And if it is, then along with the last 4 packets received, it has 5 new packets.
Oh, you mean like, I got your idea, like, so you mean like, because the receiver has already received like 4 packets, and if the incoming one is lost, it will just need to wait another 1 packet, right? But what will happen if we lose more than 1 packet during the transmission because of the congestion?
I think in the case of congestion,
Mm-hmm.
really TCP, when it sees congestion, should only be back off, sending last packet.
It will resend it again, right?
Yeah, later.
Right. And also, during the waiting time, because the TCP itself is trying to counting down, I don't mean it always happens for JK 2009, but it will possible that it means timeout, and then TCP go down to slow start. And under this condition, this hurts the TCP throughput drop significantly. Yeah, that's why like we have like enhancement. Yeah. So does it work for you? Or maybe we can discuss
Yeah,
like,
depends.
okay.
What is the x-axis?
The x-axis is the link bandwidth for the Y between the access point and the receiver. And the average for the X is fixed to 10 gigabit per second. Yeah. So then now let's see how the bandwidth is fair shared among the SRNC flows and the cross traffic. Here we consider that 2 sets of TCP flow. One is cross traffic, one is with SRNC. So you can see the x-axis. One is SRNC. We call it TCP, and cross traffic TCP. We just say it's cross traffic. And the before and after is before the bandwidth fluctuation occurs or not. And too easy to understand, to see in the figure, we normalize achieve the throughput by the multipath routing, the MR scheme. And this can be found in this figure that before the channel fluctuate, both TCP and SRNC and the cross traffic works properly because there won't be any bandwidth shortage. But when the link bandwidth fluctuation occurs, we can see the enhancement for the SRNC flows. However, for the cross traffic itself, it was not hurt. But it means the SRNC, although it sends some redundant packets, try to recover those lost packets, it won't sacrifice the bandwidth for the cross traffic itself. That's how the fairness is shows among the SRNC and the cross traffic. And people may argue that, well, Chinya, you just try like one simulation topology. We don't know what will happen, how effectiveness for SRNC in different topologies. So we kind of generate like these 7 topologies. Like some of them would be just simply 2 disjoint paths. Like, because some may say like, oh, you kind of cheating because you use some like join the link and then try to increase the diversity for the transmission. But then we can see like how it performs if there will be just pure, simple like disjoint path, which is more similar to what we used to work for the multipath routing. So here I just use the example for the similar to the fairness part, like to see how the SRNC enhance the throughput while we still try to sustain the performance for the cross traffic. And similarly, the before means before the bandwidth fluctuation occurs, and after means after the bandwidth fluctuates. So we can find that SRNC can still like get benefit from like different network topology. I mean, from the spare bandwidth in different network topology, while sustain like the fairness for the cross traffic. And as mentioned previously, you can see here would be just simple 3 disjoint path, and it can still increase significantly as long as there is available bandwidth in the network. So for the previous like 3 scenarios, we just test the functionality for the SRNC. And you may ask like, Qingyao, you are just talking about something not related to the wireless. So now let's see how the SRNC performs when the link bandwidth like introduce the wireless loss. And normally we just modify it as assume the link bandwidth has a loss probability P, which is like for each link independently. And we can find that it is expected that with the increasing of the link loss probability, the throughput drops. And because the SRNC tries to explore the spare bandwidth in the network, and the achieved throughput is much higher than the rest of 2 schemes, because the MR, for the MR itself, it's almost reached 0. And that's why I didn't show it here, not because it's reached more than 700 megabit per second. That's why I hide it. It's impossible because it's just pure multipath routing scheme. So based on the description for the presentation up to now let me like conclude some words, conclude the proposed SRNC first. So you may heard a lot. SRNC does perform pretty good to enhance the TCP throughput in the presence of cross traffic and also when the link bandwidth fluctuates. And as mentioned previously, the TCP drops significantly when the link bandwidth increases, and also like link fluctuation involves during the transmission. And this will comes to some ideas like bandwidth delay products. And this idea will be mentioned later for our extension work for SRNC. I will mention later. So, and in addition to just enhance the TCP throughput, SRNC actually it is integrated into existing like a protocol stack between the MAC layer and network layer without changing anything we use today. And it can be implemented distributed, which means I remember someone that person is asked that like how the intermediate node perform network coding during the transmission. Yes, if some node may be deployed by other carrier or other network provider, it may not have network coding or SRNC implemented, but it will just do the pure like packet forwarding, which won't affect the operation for SRNC in each intermediate node or in each mesh node. So based on the SRNC, because people may argue that network coding is not like practical, it may become the bottleneck of the transmission in the network during the transmission. And then we like implement, because we kind of lucky to get a G project, and we implement like a simple just linear combination for network coding scheme in the NetFPGA, which everyone must work on that must work on that, like OpenFlow a lot. It's kind of implement OpenFlow functionality in the FPGA board, try to speed up the process. And based on the experiment, like here would be just a simple experiment that we do. Like we have two net FPGA cards. One implement just pure network encoding. The other is for the network decoding. And then we measure the throughput with and without network coding. Actually, because in hardware itself, network coding can operate in the line rate, and then the throughput won't be affected. I mean, it gets slightly delayed, but it won't like affect the throughput from gigabit per second down to like a kilobit per second. Yeah. And as mentioned previously, when the link bandwidth increased to gigabit level, the bandwidth of this product increased significantly. And we find that for the underwater communication, like although the data rate is pretty low, but it has much longer delay during the transmission. So it also has the property for large bandwidth delay products. And then we adapt the SRNC and and then apply for the underwater mesh network and measure that it still can also like enhance the TCP throughput for the underwater transmission. And this work is published in the JSAC 2011. So up to now, like SRNC just mainly used for the wireless mesh network, and then for TCP. And so we are kind of think like, so what can we do next? Can we apply the SRNC to like a cognitive radio enabled network, because it has like a significant bandwidth variation if the primary user take the spectrum away. And for the data center, since it needs to like support high reliability, can they get benefit from SRNC? That's like what we are still like think of and try to investigate. And also, as mentioned previously, now people tries to download those, access to the network for real-time applications. For TCP itself, it doesn't specifically to prioritize, it is real-time or it's not real-time. But for real-time applications, it does sensitive for packet delay or packet drop. So in order to support that for future, maybe the SRNC needs to further do some better buffer management to sustain the performance for real-time traffic. And now the SRNC only designed for TCP flows itself, because like when you like open the Wireshark, you can see like about 80% of the traffic may be just TCP. That will be the main reason why we choose TCP, not UDP. And so what will happen in the future, because TCP, the congestion window, this kind of design, give wireless transmission or some other purpose like hard time. And in the future, maybe more and more people want to use non-TCP protocols. Under that condition, how could they get benefit from SRNC? That would be maybe interesting things to investigating further. And there will be maybe some other applications or some other things we can look into based on the current work. So, does anyone